into the field. His innovative work includes a patented method titled A Method of Developing Graded Nano and Microcrystalline Composite CVD Diamond Coatings for Tribological Application. A dedicated member of a scientific community, he is a life member of the Tribology Society of India and the Materials Research of India. His contributions have been recognized with prestigious awards, including the Early Career Research Award issued by the SERB PST in October 2006. Beyond his research includes the faculty roles at GM of Technology, research at IIT Madras, research fellow, industry expertise, services, and Sandvik Materials Technology with a rich blend of academia and industry. Ravi continues to put boundaries in technology. Thank you for giving me this opportunity. Welcome you, sir, for the first session of our ATAL FDP. Welcome, sir.
Thank you, sir. Shall I share this?
Yes, sir. Yes, please.
So, are you able to see my screen, sir?
Yes, sir.
Yes. So, sir, just I want to ask how much time I have so that accordingly I can plan.
Yeah, it is till 7:30 the session, sir. Maybe you can complete it some 10 minutes before so that we can have some interaction with the participants.
Okay.
Yes, sir.
So, good evening, everyone. And I thank the coordinators for giving me this opportunity also, and I thank Dr. Sriram Garu for reading the biodata. Thank you very much. So, today's session is on duplex coatings for high performance wear and corrosion applications. So my research expertise, as sir mentioned, it is like mostly I work on tribological aspects, and also recently we started working on corrosion also. Like because most of the components in harsh environment side they're exposed to critical wear as well as like corrosion environment. So most of the coatings designed for wear also they should have corrosion resistance. Because there's no like very rarely any application subjected to wear, but it's not subjected to corrosion. So it is very clear, any component you are designing for wear means automatically it has to be designed for corrosion. But whereas for corrosion is not other way, because many applications are there in chemical industry, mainly they're designed for corrosion resistance but not wear resistance. Okay. So the major emphasis on wear, and at the same time we have to understand. I mean to say, suppose you do some modification to the material to improve the wear resistance. Okay. But at the same time, how that modification is affecting the corrosion resistance also we need to evaluate. It should not happen like wear resistance is increasing, but its the corrosion resistance is decreasing. Because like many, it may happen like that. The process which we do may improve the wear resistance, may decrease the corrosion resistance. So one has to take in care, when you're designing a part for wear, and also it is corrosion resistance also taken care. Okay. That is a very basic background of this work. And I mentioned duplex coatings. It is actually a very broad term. Okay. Like if you see the literature, people define this duplex word differently. But in this context, of surface engineering, I mean to say that, if you're applying more than one process, okay, on the surface, then I call it as duplex coating. It's not necessarily you're doing double layer, triple layer or something. You apply any two process, more than one process, Either it is a coating and heat treatment, or chemical process, then heat treatment, or heat treatment, chemical process. You do any more than one process, just I'm calling it as a duplex coating. Because you're doing a process differently at different times and different places. So I'm calling it as a duplex coating. Okay. So this is the scope of the today's presentation: duplex coatings for high performance wear and corrosion applications. Okay. So this is the overview of the today's content. And now coming to the next, this topic broadly comes under surface engineering. Because like as a mechanical engineers, we know, it is like design is a specialization, manufacturing is specialization, thermal is a specialization, like a broad category, where many research activities goes. Same way, this particular topic which we are going to see, this comes under a broad topic, surface engineering. Okay. So like you can see the ASM handbook definition also, it is like the defined, right? Treatment of the surface and near surface regions of a material to allow the surface to perform functions that are distinct from those functions demanded from the bulk of the material. It is a straightforward definition. Most of the components, right, any application you take, the surface characteristics requirement is quite different from the core of the material. That's obvious everywhere. Suppose you take a gear. Okay, so gear, if you see, right, the gear body, right, is inside the core. It need to have high strength and bending moment, so it should be able to transfer the force, right, from one gear to another gear, I mean, transmission purpose. But at the same time, right, surface has to be taken care because the gears roll over each other for longer time. Okay, maybe small amount of sliding may be there. The surface is subjected to severe pitting or some other type of wear. Okay, so it means you treat the surface separately. Means surface should have different properties. So that's what actually they mean. You take a simple cutting tool, right? On the surface, it should have very good wear resistance. Okay, wear may happen because of the abrasiveness, or it may be because of diffusion, or it may be because of chemical, or it may be because of some other reasons. Okay, but as a tool, it should have high strength, but at the surface, you should have high wear resistance. Okay, so it is sometimes, right, the other properties like fatigue property is there. So generally, at the moment we see it is a fatigue rate, we think it is like a property of the core. Okay, but actually, if you see, right, how the fatigue fracture happens, it happens from the surface. So, so the fatigue resistance, right, fatigue life improvement, it comes under surface engineering. Okay, just I want to give, I just underline that anti-fatigue, right, because fatigue property comes as a surface characteristic, because you have to protect the surface a lot, right, such a way that, right, cracks doesn't even initiate on the surface. Okay, so mostly it is about the wear and corrosion. Most of the surface engineering deals with the wear and corrosion. So though there are so many terminologies are there. Okay, so just write wear and corrosion is very basic things which a mechanical engineer can understand. Okay, so what we do, right, we use many number of techniques. Okay, so many techniques are there, surface engineering, and the surface engineering as a broad area doesn't come under any specific engineering discipline. Suppose we say mechanical engineer, metallurgical engineering, physics, chemistry, right? So there is no like a specialization like a branch, engineering branch like surface engineering, because, right, the surface engineering is there everywhere. Okay, it is there for mechanical engineers also, metallurgical engineers also, even chemistry people, physics people, okay, even electronics people, VLSI people, everyone has to deal with the surface engineering one way or other, because functional requirement is different. Okay, so here, right, just I give a brief classification of how mechanical engineer sees a surface engineering. Okay, so this is a broad classification of the surface engineering. The first one, right, you see that the base by changing the surface metallurgy. So that's a metallurgy means simple is a heat treatment. Okay, so this is very basic, right, that we study there in the engineering metallurgy course. Means just only change the surface properties by changing some surface phases. Okay, means I think everyone know, right, that on the surface we try to get a martensite, then we get a better hardness. Okay, that's a simple thing. Okay. So next one, right, there by changing surface chemistry. Okay, there are some materials like steels, right, the carbon is not there at all, then you cannot convert to martensite. In such case, right, you have to change the surface chemistry first, then you have to do the heat treatment. Even you can call it as a duplex treatment. Okay, so though generally we don't use that terminology in this case because it's very common. Okay, means like first you diffuse either carbon, nitrogen, boron, then something like that, then you do some heat treatment, so you get the surface properties. Okay, and the other one, right, by adding a surface layer. Okay, means you can add, right, small layers from few nanometers to micrometers, millimeters, and right, you can add even thick layers. So here there is a very good scope for the duplex methods, because, right, more than 30-40 techniques are there to add some layers on the components. Okay, you can play with different techniques in such a way that it performs extremely well for both wear and corrosion applications, where you have very good scope for producing duplex coatings. So if you see the first three, right, you're doing some modification either metallurgy, chemistry, or you're adding some layer. Okay. In surface engineering, right, there is other techniques also there, right, where you treat the surface mechanically. I mean, like you induce some plastic deformation. Okay. Either not without any heat, also you can induce plastic deformation, like a short cleaning process. Okay. That I'm going to show, right, very brief information on that one later. Okay. Or even like a process like friction stir processing. Okay, where you still the surface of the material by means of frictional heat. Okay, like it involves like a hot deformation process, not exactly like a low temperature process, is a high temperature process. Okay, so this is the broad classification, right, where any mechanical engineering right background right person can understand these techniques. Okay. So same thing that I'm putting in with the schematics, right, where surface require different characteristics like friction wear, okay, oxidation resistance, corrosion resistance. Okay, sometimes, right, you need a protection from the temperatures. Sometimes we do only surface engineering for the decorative purposes. Okay, so below, right, I shown some techniques, right, based upon the classification, based upon the what you add. Okay, so here you can see the first one, right side first one. The right side first one, you can see that it is you're not adding any layer, but it is like, right, you do some heat treatment by metallurgy change, or you add some atoms, so you get the required properties. Like that, if you go from right to left, right, you can see thin layer to very thick layers. I told, right, more than 30-40 techniques are there which commonly used in the industries. Okay, so what I'm going to do, right, before showing any case studies, right, for the duplex coatings or composite coatings, I give a very brief overview of different commonly used surface engineering techniques in the industry. Okay. So surface modification by heat treatment. Okay. So this most of us we know actually, right? You do only heat the surface and quench quickly. Okay, so you'll be getting some surface modification by metallurgy. Okay, so just we will see a few techniques on this one quickly. Okay. So if you see this heat treatment, right, especially for the wear resistance, though we have so many engineering materials, right, not all respond the way the steels respond. Okay, the reason, if you see, right, most of the engineering components are made up of steels because they're easily available material. Okay, it's not a strategic material. It's not specially designed for high performance. It just is a easily available material, low cost material, but it responds to heat treatment well. Means you can tune the properties, right, from very low to very high. If you see, right, yield strength can be tuned from as less as 350 megapascal to you can take up to 1600 megapascal. Okay, so there is no other material, right, it's possible to change the mechanical properties through heat treatment or any process. The way, right, the steel responds, no other material responds. Okay. That's why, right, it is considered as a very important material. So though we ignore because, right, it is commonly available, but it is, right, it is a amazing material, right? You can tune the properties like anything. Okay. So that basic what is it? The microstructural changes just I am shown, right? Just now I mentioned, right? We get hardness because of the martensite. Okay. So means like basically you'll be having a ferrite, then you heat to very high temperature, so you get the austenite. That is means above critical temperature you heat, you get austenite. Then you quench. Okay. Then you get the martensite, which is the hard phase. So you're getting the surface hardness. Okay. So when we talk about surface engineering, right, it's not about bulk heat treatment. Only surface we heat and quench. Okay. Means you have to take care that, right, the bulk of the component is not being heated. Only the surface is heated and quenched, so that you get only surface hardness. There are multiple techniques are there, just but I will be showing only, right, as I mentioned, right, only for you to get some idea. Suppose if you are not you studied long back, or if you don't have the background, right, you can understand what is surface heat treatment. Okay, so you can see here, right, in this picture just I'm showing you. There are some other techniques like flame hardening and all. I'm skipping because no one are using those techniques. But this is the induction hardening, right, most commonly used, okay, in the industries. Means just they make a coil, right, out of copper, and they use the induction principle. So I don't go into the induction principle, but it is just by this whatever you see the coils, right, is made up of the copper. Okay, and right, is a, like you can see actually, right, is a water coolant passes through these coils. Okay? But thing is, it's a indirect heating because of the EMF, right? The coils doesn't heat it up. Okay, because the EMF, right, your middle itself directly get heat. It's not like middle transfer from. Generally, we think, right, heating elements are there, right? Old stoves and all. If you say it means heat will be generated first in the nichrome plate, then the heat will be generated to the material. This is not like that. Okay, induction, the main difference, right? Heat is not generated in the coil. Okay, because of the EMF, right, your material gets heated up. Okay, so one thing everyone should know, right? Very important to control the rate of heat such a way that, right, the bulk of the material is not get too much temperature, because, right, when you quench it, your core also become hardens. You can see the left side bottom figure, right? The rod at the middle, it is having just, it is a low temperature. You can see it is a black color is there. Means it's not heated so much. Only surface is heated, then immediately you quench it. But the obvious problem, right? The rate of heating in induction heating, right, is less. So while you are heating the surface, right, core also gets heated. With so much heat will be efficiency, right, it decreases a lot, because, right, you don't want to heat the core, but you end up in heating the core also, but not to the temperature where it can convert to martensite. Okay, so this is a very basic background of the induction hardening. Okay. So another, right, in the same surface hardening only for the steels, but there is a different techniques are there, especially in the aerospace industry, right? You cannot use the induction hardening where a lot of heat is going to the parts. Okay, where they need a very localized surface treatment. Okay, so heat affected zone has to be as less as possible. In such case, right, where they use the laser. Advantage with laser, right? Laser is rate of heating is so high. Okay, so it doesn't require external quenching, because the rate is such a high that one, right, the top surface get heated up to 1000. By the time your laser moves, right, it will be cooled down to room temperature, because, right, your base of the component absorbs that heat. Okay, so there's no external quenching is required. It can be very localized. It can be very localized, and it can be, right, you can repeat it multiple times with the same accuracy. So, but it is an expensive technique. So, right, only aerospace industry people, like, they use this technique. Okay. This is very basic of that surface heat treatment by surface heat treatment. Okay. So, in case of laser, right, you can use electron beam also. Okay, but it is like the purpose is different in that case. Okay, we don't go in details that much. And sometimes, right, the steels, some steels are there where it's not containing the carbon. But everyone knows, right, martensite cannot be formed without the steel is not containing the carbon, because the diffusionless transformation happens only, right, your carbon is diffused into the austenite, then you are quenching it, then diffusionless transformation happens, then right, as there is no diffusion, your BCC become to BCT, right, you are getting martensite. Okay, if the carbon itself doesn't exist in the steel, okay, there's no way you can heat treat it. In such case, right, where there are some techniques are there, like, right, you diffuse the carbon into the surface, then you enrich the surface with the carbon, then you do the heat treatment. It is same as like previous process only, but thing is that in this material there is no carbon before, so you're diffusing the carbon first, then you're doing the heat treatment. Okay, it's a simple heat treatment technique, right? We call it as by changing surface chemistry. Okay, so you can see it as a duplex treatment, because you are doing two processes. One is you are diffusing the carbon, or you can diffuse nitrogen, or you can diffuse boron. Then you do the heat treatment. Okay, in some cases, if you're diffusing a nitrogen or something, that heat treatment, separate heat treatment is not required. But if you're diffusing carbon, okay, just carbon only occupies the place. Again, you have to do the heat treatment separately to get the required properties. Okay, so that is like one part, like where you're using heat to change the surface properties. As I mentioned, right, I'm not giving much details because we have to do case studies also. So I'm giving very brief information quickly. But next is, right, that is the surface treatment by plastic deformation. So means if you see this word, right, there's no heat allowed involved. Only you modify the surface by plastically deforming it. Okay, it's like a cold working process. Okay, so especially, right, there is only few techniques are there, right, which is considered surface engineering. It's not like a forming process or something. Okay, please remember, only you're doing a surface modification, not to change the shape or size. It's only to induce some compressive stresses. Okay, or sometimes you use some process, right, to reduce the grain size. Okay, so what we are seeing here, right, there is a short pinning process, a SMAT process, laser shock pinning process. Okay, so we don't spend much time on this one, but just everyone should know, right, this type of techniques are there in surface engineering. But as I mentioned, right, fatigue life can be increased by only surface engineering process only. Because if you see the fatigue failure, how it happens, right, the micro cracks available on the surface during the cyclic loading, they keep growing with time. Okay, that is where actually the fracture happens, fatigue fracture happens. It's not like it's a bulk, it happens from the center or something. It happens from the surface. So it is considered as a surface. By improving the surface characteristics, right, you can improve the surface life. That is the reason that most of the automobile rotating components, springs, all are, right, treated with this short pinning process. Okay, means you induce compressive stress on the surface. So any micro cracks on the surface, right, they'll be get closed with the compressive stress. So the life of the part increases by 100 times, 200 times. Okay, so it is like a major difference in the part life you can see by these techniques. So it is very commonly used in automobile industry as well as aerospace industry. The first one which you see, short pinning, right, it is very commonly used in automobile industry, but it means the only thing you cannot control the shots the way you want. Okay, but the other one, right, laser shock pinning, similar to laser heat treatment, right? So this is also very expensive process, but aerospace industry, they use this laser shock pinning process because you can control, right, deformations accurately and without any reliability issues. Okay, it's like you know exactly what you're doing when you're using a laser, because the power of the laser, the position of the laser head, you can control a lot. Okay, so that's what actually you see right here. It's a short pinning process. So I'm not going into much details of those things, right? What is the critical velocity and all those things. Thing is, right, whatever stress the ball hit and induce, right, it should not go above the yield stress. Otherwise, right, it produces the micro cracks. You're damaging the surface. Okay, you just write. Means you'll be inducing deformations, but you're not ending up any cracks. Okay, the stress will be, right, definitely more than yield strength. Then only, right, you can make the indents, like the way you see the compressor stress are coming the right side figure, because the stress induced is more than the yield strength. But whatever is the leftover residual stresses, they're always the less than the yield strength. That's what actually I mean. Okay, so I don't go in detail right how compressive stress is being generated. Actually, it is because of the balancing, how the distribution of the implied stress, right, changes from surface to deep inside. Simply, right, if I want to explain, if anyone want to know the mechanism, right, when surface hits the ball, right, see, ball is, right, is a point contact. Wherever if the surface it is hitting with less area, right, you'll be having more stress. But if you go deep into the material, right, the stress distribution, right, expands, and the area, right, more area is exposed, and the stress keep decreasing at the bottom. So in the process, what happens, right, on the surface, the stresses are more than the yield strength. Inside the surface, the stresses are less than the yield strength, which is elastic strain happens. Okay, so because the elastic tensile strain on the top, it is plastic deformation, right? At the end, right, it ends up with a compressive stress on the surface. This is a simple mechanism, right? One has to understand separately. It's not that easy, like as I mentioned, right? If already you know, right, how the stress is being generated, then you understand what I'm telling. Otherwise, you need to spend more time, right, to understand how the compressive stress will be generated. So I have one custom GPT designed for this particular topic, surface engineering. I'll be sharing with the coordinators, right? Just I request coordinators to share that one with them, so that if they want to know about any of the process, so they can get the details from that custom GPT. So same thing, right? I mentioned, suppose if you see the previous process right here issue, when the balls are going hit, right, there's no control where the ball is going and hitting. Same place, right, the ball may hit multiple times, right? which is not considered as a reliable process for the aerospace industry. That's why they use this laser shocks. Okay, they use laser not for burning or something like that, but induce the deformations, plastic deformations. The principle is same. Instead of using a ball, you're using a laser shock. It means it creates a pulse as a shock wave. Then you will be deforming the material. Okay, plastically deforming the material. Okay, so it doesn't mean laser is using means that you're heating or melting. No heat is generated. Okay, we don't go in detail, but you can see that, right, to protect the surface, you have some water curtains. Okay, because the shock, whatever it generates, it should not go out. Okay, it has to go into the material. So for that, they'll be using a small water curtain. Okay. So the next category, right, is the thermomechanical treatments. See, first one we have seen heat is involved. Next process we have seen, right, plastic deformation is involved. Okay. Now here are a few processes are there where heat and plastic deformation both are involved. Okay. I think most of you, if you're doing research in the surface engineering, right, you hear these techniques very often, like friction steel processing, friction surfacing, right? These are very two common processes that comes under in surface engineering, right, where you use heat through friction, okay, and you do the solid state deformation of the surface to get the required properties. Okay, using this process, right, you may refine the surface grains, or even you may produce some surface composites also. Okay, so it's not exactly a duplex process, but you can multiple times you're doing it with different parameters, and even you can consider this as a duplex process. Means like by like just I'll be explaining, right, if I have enough slide for that. See, plastic deformation and grain refinement process with consumable tool. There is actually friction surfacing. See, in this two processes, the small difference is there, where in one case, right, tool is a consumable, similar to your welding process, right? In another case, right, tool is non-consumable. Only it steers the material and reduce the grain size. Okay. So the process which you see here, right, is a friction surfacing process. Okay. It's not steering process, it's a surfacing process. Very right. People have done a lot of research, but I have not seen any application that where people are actually using in this industry. Okay. So they call the tool as a mechatrode, similar to electrode, right, in welding. So where I think here you can see that when the first top left side figure you see, right, a cylindrical rod is there, which is going to be in contact with the surface. Next figure you can see that, right, like a force is applying and it's being rotated. Because of the heat, right, the friction generated heat, the material plastically deforms, then it starts sticking to the base. So when it starts sticking, right, it keep building the material, means material flow happens from the center of the see, you can see that right at the bottom, like a flash type of thing, and we call it as a flash actually. Okay, because the material deformation, that because of the force it rolls back. Okay, from the center it pulls the material because of that, because center is heat is accumulated a lot at the center, so that is right, is less than the melting point, but it can flow freely from the center. Okay, so that goes from the center, it acts as a layer. Okay, so it looks like very simple, right, but very difficult to control the process parameters, because right, maintaining force constantly to required generating a required heat, right, is very difficult. Okay, there is a reason, right, nowhere you see this process often applied, right, and used for the research purpose, even unless you have a sophisticated machine to control these forces. Where the contemporary other technique you see, right, everywhere, any workshop is there, mechanical workshop is there, you can use this process. A simple vertical milling machine, a tool can be replaced with a tool like this. FSW tool is there, right side you can see, where your shoulder is there, where a pin is there at the bottom. Okay, so here the purpose is not to transfer the material from the tool to surface, but to stir the material, stirring the material. Okay, so that's what we call friction stir, right, processing. Okay, so actually, right, it is initially, right, coined for the welding purpose, right. When they understand that it can modify the surface, even not only just for grain refinement. Okay, sometimes some particles or like some phases are there which cannot be dissolved, right, in a stable condition, right. So even it can dissolve them because of the in metastable state. Okay, so secondary phase distribution can happen in the material. Okay. So it is, right, it's not like a milling process or drilling process. It doesn't remove any material. It is only touches the surface and it rotates by friction, heat generates, and it turns the material. Okay, so bigger grains will become smaller grains, and so phase distribution may happen in the material. It changes from material to material. Okay. Same process, right? We can use for producing surface composites. You can call it as a duplex process. See, here is a FSP, right? We're calling FSP. But if you, by some means, if you're able to provide the particles at the stir zone through the center of the tool, or initially relay holes on the surface and you fill some powder material, or you produce a groove and then fill the material. Okay, you can produce the surface composites also. So many people have done a lot of work, right? As I mentioned, right, this can be done in even every workshop. So many people have worked left and right on this topic. Okay, so you can see here, right, how they're doing it at the bottom. Okay, so means they're making a groove with some shaping machine or milling machine. Then you are filling with the powders, secondary phase particles. Then you are friction stir processing. Okay, so it produces surface composites. Okay, this is one way of, right, modifying the surface. Okay. So the next topic, right, which is key, right, where we spend more time, right, that is more of metallurgy related things. Okay, most of them. Okay, what we discuss here, few are related to chemistry and physics. Okay, so surface production by adding layers. Okay, so as I mentioned in the beginning, right, a layer can be as less as few micrometers to few millimeters. Okay, most of the purpose we add layer is whatever is the previous process which we have seen, they cannot protect the surface. Okay, in such case, right, you keep adding the layers. Okay, that is a very important. Otherwise, we try to avoid any adding layers, because adding layer is always a expensive process. If we can solve the problem, okay, just by heat treatment, that's the best technique. Okay, if it is not heat treatment by simple means, then you change the surface chemistry. If you're able to protect the surface, that is even like much appreciable. Okay. But if it is not possible that way, then only you go for the adding some layers. As I mentioned, that adding layers always a expensive business. Then you can see here at a hot facing dimension, right? Hot facing generally, as I mentioned here, because is more related to the mechanical means, right? It's not, metallurgy is not controlled there. Okay, you don't worry about the atoms. You don't worry about the phases, bonds, and all. It's just like a welding process. Okay, little bit it is, right. They'll be using some sophisticated welding process like TIG or plasma based welding process to add a thick layers on the surface, but it's a more controlled manner. Okay, so it means your base is a mild steel, then you can add some tool steel on the surface, or sometimes, right, some high alloy steels you can add on the surface. Okay, sometimes, right, even you can add carbides. There's rarely people do it because carbide is a expensive material. When you want to use carbide, means there are some other techniques are there for adding the carbides. Okay, you can see here cladding. Okay, cladding is a technique, right, where is a laser cladding. Actually, is a laser cladding where is an expensive process, but without wasting much material, right, you can get maximum out of the carbides. Okay, like suppose you're using a material like stellite. Okay, so you're using material some other nickel chromium based alloys, which are expensive, right? You cannot go for the hard facing process, right, where a lot of material wastage is there. Okay, where your quality of the input material decreases. In such case, they go for the cladding process. Okay, so means where controlled way you can heat. Okay, you can preserve the metallurgy of the raw material, and you can add the thin layer on the surface. Okay, sometimes that what happens, even you do cladding, hard facing, the dimensions of the part changes a lot. Okay, but if you don't want to change the dimensions very much, then you have to go for the spraying process. Okay, whereas fine particles, right, in the powder form, you spray on the surface with the help of heat. Okay, so we see those things also a little bit. Okay, the last one, right, which we see here, right, there is a PVD CVD. As I mentioned, right, layers can be added in a more controlled manner. Physical vapor deposition, chemical vapor deposition. Okay, so the PVD, right, it is I think for mechanical people, right, we are very aware of the cutting tools. So we will see that one, right, TI, titanium nitride coating TI, and TIC and TIL, and very thin layers they add, few microns. It's not possible to add using any other methods, because the layers are like in microns, 1 micron, 2 micron, 5 micron. Okay, sometimes right in nanometers. In such case, we have to use only this PVD CVD techniques. This is mostly related to the chemistry and physics related topics. Means we have to add atom by atom. You have to add. It's not like, right, you're adding a powder and melting something like that. No. Okay, you have to add atoms on the surface to atoms, keep building it. Okay, that's why the last two processes are a little bit different. So I'll be showing some slides on that also. Okay, here you see, right, one technique which I'm showing there, that is a hard facing. I'm not showing it actually. Right? Hard facing, if you see the mining industry extensively they use earth moving equipment, all the procliners and whatever you see, right, anything worn out, then they add the thick layers on the surface, because right, they don't bother much about the geometry. They have to add some protective layer. That's it. Okay, but leather cladding, right, is also a hard layer. Sorry, it is a hard facing technique. But thing is, right, it won't damage the substrate as hard facing damages. Okay, and doesn't require much finishing operation on the surface, because right, leather cladding produces not smooth layers, but it is like a reasonably good surface. With simple grinding, you can get the required finish. Okay, and here you will be using right, as a control, right, is there. You will be using argon also, so that your material doesn't get oxidized. Okay, but only thing it is here, right, there's no kinetic energy involved. The process you see, right, just you from the nozzle powder falls, then your leather heats, melts, and then it just sticks to the surface. It's a simple process. There's no kinetic energy or anything to the particle. Just it is a heat energy, thermal energy. Okay, just you're melting, but melting and cooling is very quick, because you're using a laser, so your part doesn't get heated up much. But on the other side, if you see hard facing, that you have to use some welding, a lot of heat generated on the surface, which will be absorbed by the component also. So your component may deform. In this case, that issue is not there much. Means like it's not. I'm not telling that it is not there at all, but it's minimized compared to hard facing. Okay. So you can see that it's a single clad layer. Just one of my MTech student has done this work. Okay, means he added a single clad layer with the laser. Then he's done some heat treatment. Like you can see it is like you can see on the top right side that you can see that numbers are mentioned. Non-heat treated and 475, 550, and 625 is mentioned on the figure side. Means different temperatures is carried out the heat treatment. I think it's for 1 hour. Okay, you can call it as a duplex process, because you're doing a cladding, then you're doing some heat treatment. Okay, so you can see some variation in the properties. So I have not kept much details on that one. I'm not going to discuss also, but we have studied the wear and micro hardness of these materials. Okay, where I can see here, right, I can show you right bottom side some figures, where the first graph is for the micro hardness. So compared to substrate, because right, see, substrate always the properties are very less. By adding cladding, right, your hardness increases so much. That is one step, right? There's a like very basic process we are doing it. Again, then further, right, heat treatment is carried out, so properties are a little bit increased. Okay, so though we call it duplex process, people don't call it as much like this, because right, the property variation is very less. You see that is 800 to 950, something like that. Okay, there is a marginal variation in the micro hardness, right, which unless it increases the product cost, and it causes other variations, because right, when industry has approached us to understand the effect of the heat treatment, so we carried out the study for them, but later they understood that one, right. So heat treatment doesn't adding so much value to the part, but again, it's a cost of the additional process like heat treatment increases the cost. At the same time, the heat treatment also causing the distortion in the parts. Okay, so and the wear resistance is not significantly improving it. If you see the next figure, if you see the wear resistance is the weight loss. So the weight loss difference is not so high. Means for publication purpose is okay, but to adopt the industry, right, doing heat treatment and applying on the parts is not justifiable. The next topic, right, that is instead of adding a thick layer, right, not so thin layer, but it is a controlled manner. You can add some few microns, 200 microns, 300 microns layers you want to add. 300 microns means 0.3 mm. Okay, in such case, right, you can use this type of process like a spraying. Okay, I don't know how many of you are aware of this process. Actually, it is a, in previous case you have seen that I mentioned leather cladding. I specifically mentioned we use only thermal energy. Okay, so where this is the process, right, because thermal energy, only thermal energy means lot of heat. It damages the part. Okay, even cladding damages the part. So aerospace industry, right, this process are not allowed where heat is more. But to make some material to stick, some energy is required. So this process is like coined in 1922 or sometime. Okay. So where they understood that, right, some energy can be given as a kinetic energy also along with the thermal energy. So you minimize the thermal energy and increase the kinetic energy. That's what actually they done in this HEOF process. Okay. So the temperature to which the particle exposed is like around, you can say 2000 degrees centigrade. Okay. Not like melting the particle. Okay. Because, right, to melt any of these materials, you need 3000, 4000 degrees centigrade temperature. Okay. So just you reduce the temperature, but velocity gives so much kinetic energy. Okay. Like Mach 1, Mach 2 means almost, right, in this HEOF process, right, you have a 2 Mach velocity. Means the particle flies at a velocity of double to the sound velocity. Okay. It go and stick to the surface. And the distance you can see from the gun to substrate almost is a 3 feet, 4 feet distance. Okay. Where laser cladding is a few millimeters. Heat directly transfers to the substrate in laser cladding. Here, your substrate, right, gets only exposed temperature 200, 300 degrees centigrade, not more than that one. Whereas in previous case, it goes to 2000, 3000 degrees centigrade substrate.
Ravi Kumar sir, sorry to interrupt you. There is one raised hand here. Probably he has a query. Will we take the questions now?
So I think we take at the end.
Okay, sir. Okay.
Just please remember the like slide number. So that's why I mentioned the slide number here. So
Yes,
after the session, we'll come back to the questions, and that then flow will be maintained.
Okay, sir. Yeah.
That will be better.
Yes.
If it is an interactive, personally in person, right, so then I prefer the direct questions. But online, right, always I prefer to take questions after the presentation.
Fine, sir. Fine, sir.
Slide number mentioned, so I request the participant to note down the slide number so that, right, we can quickly go to the slide and we can discuss at the end after completing the presentation.
Yes, sir. Please go ahead.
So there are many applications, very extensively used process. It's not like a new process or something, right? But it is a already like in power plants, in all industries, aerospace, power plants, industries, most extensively used process. Even in the steel roll side, in the steel plants, I mean, like rolling the sheets and all those things. This is extensively used method. Okay. So here also, right, a duplex method scope is there where whether we can heat treat the surface or not. I mean the coating. Okay. One of my PhD scholars extensively done his research on this particular material, tungsten carbide cobalt. Okay. So how much we can improve the properties? What way we can improve the properties? Okay. Even like you can say that one, right, carbide coating is one method, then you do the heat treatment. So one literature paper, you can see the left side. Left side, bottom one bar graphs are there, right? I don't know. Cursor you may not be able to see in the screen sharing, but you can see left bottom side one graph is there, where you can see, right, the first 3 bars, I mean first 2 bars. Okay, so there's no oxidation. They're going up to 350 degrees centigrade. There's no oxidation. Means the carbide, right, is stable up to 350 degrees centigrade. Means this is very well used up to 350 degrees centigrade in any environment. But this particular study that they have done, 2 ways: how much temperature this part can be exposed, and what phase changes happens in the material. Okay, but from this, right, they understood that above 350 you cannot use this material, but in a controlled environment you can do heat treatment up to any temperature up to 700, 800. My scholar has done the work on this one. Okay, if you're using argon environment and you're doing heat treatment, right, you see a very good improvement in the properties. Okay, up to, right, I'll be showing some slides if I have. See, one of the study this my scholar has done, where he studied, right, he's done 2 processes, even heat treatment by increasing the temperature as well as cryogenic treatment. See, he mentioned duplex word here, right, because duplex means he has done heat treatment, then also he has done the cryogenic treatment at different durations of time, right. He dipped the sample in the liquid nitrogen. Okay, so we don't have any controlled cooling method. So, right, we call it the deep cryogenic treatment. Means you're directly dipping the part in the liquid nitrogen. So for mechanical engineering people, it is okay. People don't have to object. But if you want to do a systematic study, right, it is expected to cool the part in a controlled manner. Okay, so like 10 degrees per minute or something, slowly you cool. So for that, right, you need a different system for cryogenic cooling. So that we have seen, right, some improvement is there. Okay, even after heat treatment, even after cryogenic treatment in the wear resistance, but not that much significant compared to the costs involved in the process. Okay. Corrosion, right, also we have seen, see, corrosion again is a surface property where it's not a harsh environment we studied. We use only, right, electrochemical workstation, right? So for the given time, whatever we have done after corrosion treatment, we have seen a lot of improvement in the corrosion resistance. So we studied the whatever compounds that form after corrosion also with the help of Raman spectroscopy. Okay, so we see a very good results. Okay, this data is published well in various publications. Okay. So the next topic, right, adding thin layers of materials. Okay, so right, just currently I'm not working on this particular topic. Actually, this is like what I'm showing here right now. It's like based on my PhD work that I have done, because it is very interesting, and till now whatever we discussed, right, there's a very common and which we can everyone can do everywhere. Okay, where however this thin layers handling, right, and we see that high-end applications like cutting tools and right. Even watches, okay, which does not come directly under the mechanical stream. Okay, we don't explore much, but I got an opportunity to work with the physics department where I done some work during my PhD. Okay, just I'll be throwing some light on this side so you understand some basics of this PVD and CVD process and how tool coatings are done. Okay, cutting tool coatings are done. I'll be showing some pictures also. See, PVD, right, there are two techniques are there. So I don't explain process much, but I tell you the difference, what exactly PVD and CVD process. See, PVD is, right, it is a deposition process where atoms go and sit on the substrate or tool, whatever it is. Okay, so where there is a very good scope for getting a sharp cutting edges. Wherever a cutting tool required a sharp cutting edge, we will go for this PVD process. Okay. The another one is CVD, is actually the growth process. Means the growth happens from the surface. Compounds keep generating from the surface, right? Wherever temperature is more on the part, there more material grows. So getting a sharp tools is not possible in the CVD process. There's only basic difference there which we should know. Okay, I'll be showing some slides here. See, what you see here is a sputtering process, physical vapor deposition by sputtering. So as I told, right, it's not like you're adding a particles or melting some powders or material. No, you deposit everything atom by atom. Okay, so it takes a lot of time, like to get like 1 micrometer also you may need to take like 1 hour, 2 hours. Okay, sometimes even more, depends upon the which process you use. Okay. So it means like use a heavy atoms and you give some kinetic energy because of the and by giving the what is that? The charge difference, right? You'll be accelerating argon type of particle on the surface where it goes and hits the surface atom, not particle atom, sorry, and it plugs the other atoms. The atom will go and deposit on those things, other whatever component we want. So for explaining the right, I made it very simple, but it's not that easy that process to do actual component. But this is a PVD process where you do atom by atom. The another one, right, which I'm going to show some experiments also. There's the chemical vapor deposition. Okay, suppose any material can be generated by using some gases. Okay, so means like you are using some gases which is containing some metals. Okay, so in this case, what I'm going to show you, right, it's only right is the diamond, so is the carbon containing gases are good enough. Otherwise, any type of coating can be done using some even gases. Okay, means you heat the gases, they decompose. Then, right, I think it's actually decompose not correct. Towards the pyrolysis may happen. Then it is you'll be the reactions happens in the inside the chamber. Then it deposit as a grow or deposit. There are so many small variations there. Homogeneous depends upon the whatever chamber you use it. So we don't go into much details. But there are, right, it is more complex than a PVD system. Okay, more complex than a PVD system. Understanding the chemistry is more important, how the reactions taking place. Okay. So this case study, right, which I'm going to show you, right, about the cutting tools, where how we can coat high performing duplex coating, especially diamond coating on the cutting tool for machining tough to machine materials like aluminum, silicon carbide, metal matrix composites. Okay, see, aluminum is right, soft, okay, easy to machine, but there are some other issues like sticking to the surface, but the tool doesn't get worn out if you machine only aluminum. But some applications in the aerospace industry, automobile industry, right, where their aluminum is right combined with the silicon carbide. Okay, and silicon carbide hardness is comparable to your cutting tools, any of the cutting tool. So when this particle size is so big, right, relatively like 20 microns, 25 microns, very difficult to machine with any cutting tool because the particles will abrade the cutting tools and get worn out. Okay. In such cases, right, where there is no other option, then only people go for this diamond. Okay, diamond as a coating. It's very simple. Okay, because diamond it doesn't go unless otherwise, right, there is no option. The diamond coating is an expensive process. Tool cost is so high. And it is very fragile also. You need a very sophisticated, stable equipment to conduct the machining process. Okay, so I don't go much details in the actual process, but very simply I explain. Diamond is nothing but it's a carbon, but it's a sp3 form. Okay, so based upon the phase diagram, right, they understood that, right, some temperature and pressures you can convert this carbon into sp3 bond, that is diamond. sp2 is graphite. Okay. So they use this methane gas and then expose the methane to very high temperature, 2200 degrees centigrade, right? Then you'll be forming carbon radicals. Once the carbon is formed, right, it forms both sp2 bond and sp3 bond. Okay, but you need a sp3 only. I mean, that is sp3 hybridization. We call it diamond on the surface. Okay, so and you don't want graphite in that one. So that's the reason that they send the hydrogen also. Okay, hydrogen is a typical characteristic, right? It eats away the sp2 bond. Okay, so we don't go in detail much at how the linkages happens. The hydrogen atoms, right, we go and react with the sp2 bond. It takes away that one. So right, you end up in only sp3 bond lying on the surface. Okay, so you get diamond on the surface. Okay, and more than that, right, and also there is multiple ways are there to control how even diamond is growing. You can see at the bottom right side, two figures are there where the diamond is very small particles, a small growth is happening there, whereas the other case is a bigger growth is there. So we can coin them as a NCD, means nanocrystalline diamond. The particle size is so small, right? The whatever is appears on the surface, then we call it as a nanocrystalline, less than 100 nanometers. Okay, but it's bigger than that one, like 1 micrometer or more. The diamond facets you see, right? Then we call it as a microcrystalline diamond. Okay, so this, right, these two coatings are having very different properties. If you see, right. So this is the equipment, right, which I used during my PhD, right, for developing the coatings. So why I mentioned, right, generally we cannot do this process because this equipment are so expensive. Okay, so at that time it is like almost this equipment is 3.5 or 4 crores. Okay, which normally, right, we cannot afford running even in the machine. Buying is different. Okay, running the machines also so expensive process. So, unless, that's why I mentioned, unless it is required, we don't go for this PVD, CVD coating. Especially diamond, we don't go for the application. That's why you don't see. Only few industries you see like a PCB drilling. Okay, sorry, what is that? The PCB means, I think, polycrystalline board or something is there. Okay, printed circuit board. I think printed circuit board. Yeah, the electronic applications they use, right, printed circuit boards, where to keep the chips and all those things, small holes to be drilled. Okay, that cannot be done with any tool other than the diamond, because these PCB boards are made up of silicon and glass particles will be there. So any tool used other than the diamond, they get worn out. Okay, further they use PCB. Sorry, this diamond they use, and also sometimes CFRP you want to machine, carbon fiber reinforced plastic. Okay, so the carbon fibers are so hard, right? Any tool gets worn out, and sometimes getting surface integrity is very difficult with other tools. In such case, they use the diamond coatings. There are so many applications are there, and I mentioned this, right? Aluminum silicon carbide. Okay. Sometimes what happens is, instead of design the cutting tool, they design the work material. Means they reduce the silicon carbide particle size so small, such a way that, right, it does not cause wear to the cutting tool. Okay. the multiple ways are there dealing with the problems. Okay. So means you need to go for the diamond coatings. You can use normal coatings and you can machine the material. So that I mentioned, right, nanocrystalline diamond. So how it has to be characterized, right? So this is what's the right side, you colorful figure, that's the AFM, atomic force microscopy. Where the other one you see right here, there's a bigger grains. You can see 1 micrometer, 2 micrometers. Okay. The left side one is the SCM picture, and right side one is atomic force microscopy picture. So the grain size is so big. So the intention here, right, to show different properties, how the properties vary from this too. So means small microscopic variation in this material side causes huge difference in the properties. Okay. So when you design any coating for tooling applications, right, any coating you say, adhesion is more important. How it is sticking to the surface, how strongly it is sticking to the surface. If you see the top one is nanocrystalline diamond and below is microcrystalline diamond. Okay. If you see from the right side figures, right, I don't need to explain these things much because right, that is actually right. It is a scratch test when they do when the nib come in contact with the substrate surface, it behaves differently. It emits a different acoustic signal, or right, it behaves different friction characteristics. Automatically, you'll be able to distinguish where the coating has failed. Okay, if you see from the outcome of this picture, right, the microcrystalline diamond is showing better scratch resistance. It is sticking hard to the surface. Okay, the nanocrystalline diamond is having poor adhesion resistance, means not sticking properly to the surface. So why I am telling, right, so how we design the duplex coatings depends upon the properties. Means from this, what we can see is, right, on the surface you want microcrystalline diamond because it is sticking well to the surface. Okay. But if you see the next property, friction, right bottom side, you see the friction, right? Right bottom side, you can see that. Okay. On y-axis, you have the friction coefficient, the x-axis sliding distance. Okay. It's very clear from here, right? The friction coefficient is very less for nanocrystalline diamond, which you want on the top of the surface. Okay. So microcrystalline diamond you want on the surface, and nanocrystalline diamond you want on the above surface, so that you have better adhesion, better friction properties. That is why actually, right, we go for the duplex coatings or composite coating, whatever we call. Means same material but different microstructure having different properties. So you use the best of their properties. Means first you coat the MCD on the cutting tool, so it's having better sticking to the surface. On the surface you coat the nanocrystalline diamond, so it's having better friction coefficient. So you use both the properties better, and you're getting the better high performing material. So definitely people will go for this, adopt this process. This is a technology, right, which we developed. Even we have filed patent, and one of the industry now is there. Okay, in Chennai, right, Kapindra, right, they started, they adopted this technology to develop the coatings. It performance almost 3 to 4 times increased compared to independent layers. Okay. So some characterization, right, where you can see here, right, how. So I don't go much in detail this composite coating. See, I mentioned, right, how you do the coating. Sometimes what happens, NCD you're coating an MCD, like 2 layers, right? Again, top layers adhesion is not good. It may come out very easily. Even like that's what actually we understood while doing some test. Then what we did, right, top right side figure you can see. Instead of having some clear-cut difference layers, MCD, NCD, right, we developed some technique where you can transition can happen, gradient from microcrystalline diamond to nanocrystalline diamond. Okay, so in the previous figure, if you see here, right, left top left side, you can see a clear-cut difference on top NCD, bottom MCD, microcrystalline diamond. MCD means microcrystalline diamond, NCD it is nanocrystalline diamond. You can see a clear difference here. Okay, in the top left side figure. Okay, so but if you see here, right, the bottom left side figure, here there are 2 layers are there. But thing is, there is no distinguished line between nanocrystalline diamond and microcrystalline diamond. Okay, that is because, right, of the transition zone, right, which we created by the process. Okay, so to publish that one, right, reviewer has asked how to distinguish. Then we have done some Raman spectroscopy study, right, because, right, you need to find some technique, right, where you distinguish nanocrystalline diamond and microcrystalline diamond. Okay, so we use some technique to distinguish between these 2 layers. So in previous case, SCM is fine. In this case, right, we are able to see 2 different layers with Raman spectroscopy. So where you can see here, I captured some video also. where it is when changing the zone, right, you can see the spectrum is changing. So sharp peak means it is a high crystallinity is there. So where your sharp peak is disappearing means it is a nanocrystalline in nature. So that's what actually it is explains. So just I want to end the slides with this topic, right? Finally, what I want to say, right? Composite means, right, you have different techniques. I told you surface engineering, hundreds of techniques are there. Okay, you take a surface engineering handbook or you Google it. I'll be sharing some custom GPT link, right, where you can see. So many techniques are there, but based upon the service requirements, how you club, if you're able to achieve the performance with single technique, that is very good because you're saving the money, okay, to the company. But if you're able to get the better performance by clubbing more than one technique, right, then we call it the duplex process. Okay. So with this, right, just I want to close my presentation. So if you have any questions, right, you can ask me.
Participants are requested to raise their questions, if any.
You can unmute and ask.
Hello, sir.
Yes. Yeah.
Sir, actually in thermal spray coating, tungsten carbide and the chromium carbide, these are the ceramics, right, sir?
Yes,
So, is there any bonding material is required for coating of those things, sir?
Yes, definitely, right. They'll be like always, right, there. See, you take a ceramides, we call ceramides, right?
Yes, sir.
So ceramides means what is that ceramic particle and it is combined with some metals. Okay. Always some amount of metal is required. Okay. But always these materials are having higher side of the ceramic particles side, means volume wise, if you see, right. So it can have 3% cobalt and 97% carbides, or 6% cobalt, 94% carbides, or 12% cobalt, 88% carbides. So it can keep decreasing up to 25%. But what you see difference, right, is toughness and hardness. You have the more metal, less hardness, but more toughness. So you have to see that what you required for your surface. Suppose your surface also demands. Sometimes what happens, right? So some part is there, you're doing a hard coating, but also it is getting some impacts here and there. In such case, right, your surface should have some enough toughness. Okay. So, right, in that case, you will be adding more cobalt or nickel, right? You will be adding to the material. So, suppose you see that dyes are there which are made up of carbide. If you see that most of them with 25% cobalt. Because, right, dyes means what it is, you are hitting with some hammer, forging or something may happen, right? That's why you add more cobalt. But your hardness decreases a lot. And for cutting tools, you will be using 6% to 12%. Okay. Because the cutting tools, right, you have to have more hardness, and you have to design your cutting tool to get the required toughness. There's a little bit key, right? How you, right, design your cutting tool to use as low as possible the cobalt. Yes. Anything else? Is this clear? My answer?
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir.
Yes, please.
Yes,
And also, right, as you asked, right, the powders which you're mentioning, right? So they take very fine 1 micrometer, 2 micrometer particles, and they make like a balls using some methods. Specialized methods are there, right? And they make the particles are 15 microns to 45 microns. Like the powder is like in the powder size, right, varies from 15 microns to 45 microns. There in that each ball, you can see it's like it looks like a ball, right? You'll be having the binder keep all these particles, 1 micron, 2 micron particles together and keep it same. Then you are throwing them with high temperature and high velocity. Yes. Yeah. Yes, sir.
Sir, is that shape of the particle influences the performance of the coating?
Not exactly actually, but always that the process which they produce, it is spherical, and one way is important, right? They'll be using the hoppers where material has to flow. The spherical particles flow well, but to my knowledge, that the process itself they produce similar to our glass balls they make, right? How it is similar process they use, right? So whatever I seen, right, most of them are like spherical only. Okay, I mean like close to spherical balls. Okay. But if it is not spherical, then definitely it affects your flow of the particles. Uniform flow happens, right? The variation ball size they keep only for that purpose. When the variation is there on the size, right? They adjust in the voids and they flow easily, and the powder will fall down into the nozzle of the throat of the nozzle. Yes, sir.
Yes, sir. Thank you, sir.
Sir, there is a few more raised hands. Dr. Satyanarayan Reddy garu.
Yes, yes.
Yes.
Okay, sir. I got one small question. This is, of
Yes,
course,
sir.
diamond, like diamond-like coating,
Yes.
coated the carbide tip tools, or even the CVD, PVD coatings. Okay, they will be no doubt for the. They got very high wear resistance and they're longer life. They'll cut it. But I'm not talking about the cutting. Cutting, sometimes CDM wire cutting is also a very good option, even though it is extremely hard material, high melting point materials. So EDM wire cut also can do the job of cutting.
Yes, yes, definitely, sir. It is like there is only EDM, wire EDM, or telling your EDM.
Wire EDM.
So there is always, right, what is your purpose? Only to split into two pieces,
Yes.
or to get a profile, right, which is vertically aligned profile.
Yeah, we get it like tensile test specimen, vertic specimen from the cast part.
In such case only you can use wire EDM. But if you want to produce a hole or something, right, it's very difficult to produce with the wire EDM and EDM. EDM is small hole is to be produced, and EDM is better. But if you want to make some complex shapes, then there is no other method other than the diamond.
Okay. Okay.
Only in such case only we use diamond. See, sir, like your question is exactly correct. Always the manufacturer will see what is the cheapest method available to produce the right part. That is the only constraint. So people never go for this, as you mentioned, unconventional method also we don't go. Suppose if it can be cut with some other method with a saw, we don't go for wire EDM.
Correct.
So if it is not cut by other material, other process which is cheaply available, then only we go for the other higher methods, right, where cost is more, but there is no option for it.
Right. See, one more thing, sir. Your covered actually gave a very good, infinitely larger landscape of surface engineering process through the wear resistance, corrosion resistance, and things like that. Okay. So that explosive cladding is also one method by which, cheaper way of doing it on a larger scale plates, followed by the hot rolling and cold rolling to
explosive cladding.
Cladding.
Okay, I mean, like you're taking a sheet is like a explosive. I mean, like your layer you're just sticking to the surface by means of explosion.
Correct. You're basically placing a thin layer or a thicker block. A sheet, both are sheet and plate, and they're separated by small distance, and the explosive is spread over the top layer.
As I mentioned, there are so many special purpose methods are there.
Yes, sir.
So which are even like this, whatever you're telling, that even I have not heard the process, but actually, right, the moment you say explosive, I could imagine that how they're doing the process. But actually, it's very good to know it is like this process existing. I will explore it. Industry.
Yes,
and whatever I presented here today, where the process which I've seen in the industries, usually I like to visit industries every time. So whenever I get some opportunity, these are the process which I've seen physically. So I'm impressed the way how they're doing it. So I presented those things. And
one last question, sir.
Yes.
Actually, we are from the student community and faculty student community for the, looking for the point of view of the projects, small projects for the students actually. Can you suggest the places in and around, like Hyderabad, other places, where we can go for the CVD, PVD coatings, smaller substrates?
CVD, PVD, right, these processes are always very difficult to get outsourced this work. Okay. Because, right, these processes, always these equipments, CVD, PVD, they always a special purpose.
Okay.
I mean, they're designed for some purpose, like cutting tools, okay, or some watches. Means like whole fixtures are designed only for that purpose.
Yeah, but generally, sir, what happens if they got the facility, they will allow some small pieces of of the similar material kind of things.
Then that can be done only, right? Where is a research scale facility like Anna University is there. I think they will do on payment basis.
Okay.
Okay, they're having a PVD setup, but the CVD I have not seen anywhere, right, of a research lab scale equipment. In whatever I shown equipment, there is a commercial equipment actually, which is a 3.5 crores. Okay, now it is more than 6 crores equipment cost it is. So it's a commercial equipment. The CVD is not possible to produce in a lab scale level. People tried actually a lot. Even IZCAR people have tried like anything to produce lab scale, even they failed. Even I need to calculate. One PhD is called in touch with me, right? And she tried to produce like anything the CVD, but they end up in producing some other materials. Okay, so but PVD, right? In GMRIT, one facility used to be there, and I am there. Okay, I don't know whether it is still in working condition or not. And even Anna University, it is there. They extensively they do. Otherwise, sir, even you can approach this Hyundai company itself directly.
Okay, Hyundai vacuum company. Okay.
So they may do on payment basis because they have the facility for always in research lab. They may be doing. But there are so many other techniques which we can use that is easy to access. That's why actually even I shifted from CVD, PVD to other common techniques now where facilities can be accessed like laser cladding. Hyderabad, so many companies are there. Okay. And even thermal spraying companies are there. So many companies are there. So where they can do the coatings and give at very meagerly low cost. Okay. Even I get my coatings done from the Jodhpur because none of these thermal spray coatings equipment we cannot maintain it. So everything I get from the Jodhpur. So they charge per run some 30,000, 40,000 rupees, but they do the coating and they give.
Okay, sir, you have shown one graph actually, friction coefficient versus sliding distance. That is a pin on disk experimental result. There you have shown that MCD, microcrystalline diamond, and nanocrystalline diamond.
Yes.
So the NCD is at lower. What was the justification you were giving actually? Can you?
So actually, right, this NCD when grains are very small, so it is actually sp3 bond has to form, right? So the sp3 bond cannot form at the grain boundaries. Okay, it forms a transpolylacetylene. Actually, as I mentioned, right, hydrogen also there in the process.
Yeah, it will reduce.
So the CH bonding forms actually. We also call it transpolylacetylene. Okay, so that when sliding is happening, that comes readily out, and that gives you a very good friction properties. That because of the transpolylacetylene comes out, graphitization happens on the surface. Okay, because the graphitization that you'll be getting a smooth surface. I mean, like low friction coefficient. Whereas in the MCD, if you see top right, sir, it is it's only diamond. It's very abrasive in nature on surface. Nothing is there to give that resistance. Is keep scratching the material and varies more to the counter ball. You can see same thing, right? Friction coefficient is increasing after some time. The reason is the contact area increases for the ball because ball scar on the ball is so big. Your contact area increases, so automatically your friction coefficient increases.
Okay, sir. Okay. Thank you very much, sir. Thank you.
Yes, thank you.
Yeah, sir. There is one more person, Jagadishwar Rao garu.
Yes, sir.
Yes, sir. Please question. Jagadishwar Rao. Yeah.
Sir, good evening, sir.
Yes, good evening.
This is Jagadish Rao, actually, Gayatri Vijay Parishad College of Engineering.
Okay, yes.
I would like to ask 3 questions. First one is, when tungsten material is subjected for the cryogenic treatment, what are the physical properties may be changes, sir?
See, when even like a lot of review comments also we got for the cryogen treatment which done as per the phase diagram, right? There's nothing to change in the phase, but my student, right, he found some eta carbides to form or right to crystallize, and he attributed for them to property changes like hardness increases definitely.
Yes, sir.
Okay, but we couldn't find any microstructural changes, right? How this micro hardness is increasing. Okay, what exactly is causing the micro hardness increases? Okay,
except only eta formation.
Eta carbides, right? The carbide phase is changing, but it is even I am not convinced, even reviewers are not convinced, but there is no much literature available. You can go through the papers from my scholar action that actually is extensively done only for heat treatment, right? 2-3 papers we published.
Okay, sir.
Okay, so mechanical properties increases, hardness increases, even wear resistance increases. Okay.
Okay.
Corrosion, right? We cannot say even like we have shown it is increased because what happens, the corrosion increase may happen in electrochemical test, right? Even because of oxide formation, because of the corrosion treatment, some oxides form on the surface, some gaps are closed. Okay, it may be because of the these phases formed on the surface, or the gaps are closed because of because of the corrosion treatment. It may happen. But even we couldn't explain, right, because there's no microstructural change. Okay.
Okay, sir.
Yes.
Sir, one more thing. When the grain size is increases, is there any possibility to increase thermal conductivity of any material?
So that I don't think that can happen. Okay. But if it is a grain size is bigger, but the difference will be very, very less, because right, how thermal conductivity happens in material, that is because of vibrations of the bonds, right?
Yes, sir.
Okay, so that effect will be very, very less. Okay, means I have not done much study on that one, but at the grain boundary, if you have a different phase of materials,
Okay.
which thermal conductivity is very less, the secondary phases are there, completely occupied. In such case, definitely it may affect. Okay, but if it is the same material and right, just because of the grain boundary, it will not affect much the thermal conductivity, to my knowledge.
Oh, okay, sir.
The mechanism is right. It is only it is like a vibrations of the atoms, right? It just keep going. That's it.
Okay, sir.
Yes.
The next one, sir, for measuring a micro hardness of any material,
Yes.
we require 2 parameters like dwell time and load.
Okay. Yeah.
How to decide, sir, that load and dwell time for a tungsten material, for example?
Tungsten carbide, actually, it is usually done. We see literature and do. Okay, but how it is that I'll be telling you, it's actually based upon the trial and error method. See, you have the load micro hardness. If you take, right, it is a 10 newtons load to 1000 newtons load. It is there.
Yes, sir.
I mean, up to 1 kg. Okay. See, to measure, and we find micro hardness by means of measuring the indent.
Yes, sir.
So we should be able to see reasonably big size of the indent, then only we get the accurate data.
Is there any standards, sir, for that one?
No, there is no standard. Okay, but see, frankly speaking, right, even use 300 newtons or 1000 newtons, you should get the same value.
Okay.
Okay, right. But we not necessary to go up to 1000. A instrument, right, we don't use even lesser side, less than 50 newtons. We don't use. It's not accurate. Okay, but what we understood from our study, right, you should get enough decent size of the indent, which you can measure comfortably without any error.
Based on trial and error method.
Huh?
Based on trial and error method, we decide that.
Right, literature always you follow. Okay, literature you follow. Okay. For carbide, it is 300 newtons is very good. 300
newtons.
Yes, yes.
And that is the reason, sir. Why in one paper they are mentioning 300 newtons, in another paper they are mentioning the 200 newtons.
So anything, see, what I mean, say 200 newtons, suppose your indenter is good, new, and edges are very sharp, okay, then there won't be any issue, because you can make a decent indent. Otherwise, what happens, right, your edge is a little bit damaged of the indenter, assume, right? 200 newtons is less, his load is very less. So for the given load, it may not penetrate the way it has to penetrate, then it gives the wrong reading.
Okay.
So you can test it actually, right? You do at 50 newtons load, 300 newtons load. Theoretically, you should get the same value.
Okay, sir.
So you never get experimentally. So it is actually, right, it is a mechanical measurement error. Okay. So you have to do some calibration, right? You do a different loads and you measure the hardness. Okay. You see at which range you are getting the right hardness.
Okay.
So there you have to take. You understand what I'm telling it is?
Got it, sir. Got it.
It changes from material to material, whether to use the 10 to 100 or 100 to 500. Okay.
Okay, sir.
You have to see that, right, your actual value, where exactly you're getting, what is the range. Okay.
Okay.
That we get differently from the literature.
Okay.
Okay.
Sir, one more last question.
Suppose you see, some carbide, you're supposed to get a so and so value. Okay. So just because you're using lesser load, right? Some people get the hardness of some 2000 HV and all. Now you should not report it because you know that obviously it's not the actual value because you're using your instrument wrongly.
Okay, sir.
Yes, yeah.
Sir, one more last question. I have seen several semi images in your PPT.
Yes.
For the actually for holding of a sample, what should be the size of the sample, sir? Is there any standard?
See, it depends upon the size of the chamber, right? Generally, right, it has to be as small as possible to avoid any contamination to the chamber. See what happens, right? Now, most of the SCMs are field emission guns, they're using it, right?
Okay.
They don't allow any contamination to happen inside the chamber. When you're keeping a bigger sample, right, it may end up in carrying more dust and more grease or oil, anything. Okay. So
Okay.
otherwise, there is no constraint on the size unless otherwise it is fitting on the holder. Okay. That is to avoid any much misuse. That is the reason most of the institutes, right, they keep a small holder where it can accommodate in 10 mm by 10 mm, not more than that.
Okay.
So where when because right in where I've done right PhD where I operated on SCM almost for 2-3 years, we have a separate holders a bigger size. Even it can hold a 50 mm by 50 mm size part also. But we never bought that one because what happens, right? People bring big samples like tools which is having oils and all those things. It contaminates the chamber.
Okay.
Okay, so otherwise, right, there's no limit. But working distance has to maintain. 10 mm working distance you should have, right?
What is maximum distance, sir? What is the maximum height of the sample? Maximum height.
That's what I'm telling, right? How much space you have. See, working distance from the gun to your sample 10 mm has to be there. And
Minimum.
before loading, it has to be 40-50 mm.
Okay.
Okay, so it is having a bigger column, then you have bigger space, even you can give bigger. See, I kept up to, right, I think 80 mm height sample I kept in the chamber. Okay.
Okay,
But
sir.
if you ask anyone as an outside person, that I always tell maximum size is 10 mm. Okay.
Yes,
Don't
sir.
think bigger than that one. Okay. So 5 mm is a very good. Okay.
Okay, sir. Okay, thank you, sir. Thank you
Means
very
you're
much.
sending a sample to anywhere else, right, by post. Your sample should be always maximum 20 mm size. I mean, like width and height is 5 to 10 mm is a very good size.
Okay, sir.
Yes.
Okay, thank you, sir. Thank you very much.
Yes.
Yeah. One more raised hand, Pawan Rajeti. Sir, can you please unmute and talk?
Sir, good evening, sir.
Yes. Good evening. Yes.
Sir, in FSP, how the type of the groove can be affect the material dispersion, sir?
See, type of the groove means okay, means like what type of the groove you are making. See, it is we tried only with triangular groove and even rectangular grooves. Okay, so it is actually there's no much difference, right? But only thing is you have to see that how much volume you want to make.
Okay, sir.
So the basic calculation you need to do at the same time, right? By putting the powder just like that, you cannot do FSP. You have to close the surface first.
Yes, sir. Yes.
So you have to do stirring a pinless tool. You have to make a separate pinless tool where only your collar is there, right? Your what we call that one, pin and I'm not able to recollect that one. So you have to rub the surface, right, with a flat surface. So your groove is closed with the metal.
Yes, sir. Yes, sir.
Okay, then you have to do the FSP process. Otherwise, that your powder will be come out. It won't get mixed with the thing. So you have to be careful, right? Your groove depth should be less than your pin height.
Yes, sir. Yes.
Okay, otherwise you end up in leaving the powder at the bottom, in the middle, as a like it cause a lot of defects. Got it now?
Yes, sir. Sir, so some resins type material will be there for adding into the adhesiveness to that particular material, reinforced material.
No, actually, no, you cannot add because it contaminates the surface, right? You end up in getting the defects.
Sir.
So it means anything you add additional to that is a contamination.
Yes.
Unless you want it to mix with the material. You got it, na?
Yes, sir.
You cannot add any other material like resins. You cannot because right, what plastic polymer will do in the metal inside. Okay, it weakens the properties. And FSP is right more about optimization, right? How you produce without leaving any voids, gaps inside. The optimization is very important. Okay. So you can refer the papers of B. Ratnasunil. So when he used to be working in Bapatla Engineering College before, right? He has optimized process parameters a lot for both aluminum magnesium. Okay. Even like we take most of the, because we never optimize the parameters because we don't have the facility here. So we take all parameters from his papers. Okay. Then we did most of our FSP work in Hyderabad on some companies there. Okay. So we just give the parameters and per pass they charge 1,000 rupees or something. Okay. Okay. So just that how we have done. Okay. Because in our institute, milling machine were not used because right, it may damage the bearings, it may damage the spindle. Okay. So sometimes right, it may create problem for you. But it is if you have a second-hand milling machine, right, which can be converted into FSP machine.
Yes, sir. Yes.
Arvitech company is there, I think in Coimbatore. So they always like if you have old milling machine, right, they're ready to convert into FSP machine.
Sir, can you please suggest me where we can perform the tensile test for the aluminum material under cryogenic conditions, sir?
No, but it is very expensive. When I wanted to do some test, right, it is not there actually. Okay.
Sir.
So to my knowledge, it is not there. Maybe DMI, if you go to ISRO, right, it may be there. Okay, but to my knowledge, it is not accessible anywhere.
Sir.
But Instron can produce those machines because I got quote right that they're asking for 4.5 crores or 4 crores. Okay, which we cannot afford.
Sir.
Yes.
Okay, sir. Thank you, sir.
Yes.
Sir, maybe some quick questions. Asir Naidu garu, can you raise? Asir Naidu.
Sir, am I audible, sir? Hello.
Yes, please go on.
Yes, please.
Sir, good evening. Good evening, sir. Ravikumar, sir. I am the scholar of Professor Ramji Garu, sir. I am very much. Hello.
Yes, sir. Please
go ahead, sir.
We are the two scholars we attended for CFD at your institute, sir, VNIT Nagpur.
Yes.
And we
Tushar
are
Goyal,
also
sir,
got
he
two
teaches,
papers. Sir, that is reference.
Okay.
Actually, I have one problem with the buoyancy, sir. I am doing one problem. What is sir name?
Okay.
Can you give that reference, sir? That CFD, I want some. Maybe
is Dr. Tushar B. Goyal. Tushar B. Goyal.
Okay, sir. Okay. Okay,
Yes.
sir. Okay. Everybody got two papers, sir. We're all awarded, and thank you for your guidance, sir. Actually, that's one month we are.
Even I forwarded that one.
Yeah, where in item
Okay.
only we attended for your workshop, and you are guided. This is that time. Okay.
Okay.
That is
Very nice.
okay. Thank you, sir.
Yes.
Thank you for your nice presentation. Thank you.
Sir, there is one more question in the chat box.
Yes, sir. Please read it.
From Dharamvid Dikshit. He says, good evening, sir. Can you please suggest any future scope in surface treatment of aluminum or titanium with nanoparticles using FSP?
Titanium is very complex to stir. Okay. I mean, like unless you have a dedicated friction stir processing setup, we cannot stir the titanium. Okay, because of its high strength and low thermoconductivity. If you try to stir titanium, what happens that immediately your tool dissolves in the material. Okay, so titanium stirring means you need a different tool materials and cooling strategies, even higher loads. It is so complex. Okay, so titanium always right. Almost we cannot do in India. I have not seen anyone doing stirring of titanium, but in foreign countries, right, they're done. We need a very expensive setup for that one. Okay. For aluminum, right, definitely, right, scope is there because even like when we started, even we thought that what is the scope, but we tried with right molten disulfide to get the good distribution. So we have to identify some gap readily, right? Even I cannot say that one, but you have to see that what is the issue. Always the issue is the distribution of the particles. If you're able to find some way how the particle can be distributed uniformly in the surface, okay, then even if you're able to produce a surface, right, without any defects, even it is a very good thing. Okay, and sometimes right, some materials cannot be like a 7075. Okay, aluminum. It's not easy to stir. Okay, easily, right, you get grooves and even you're not able to get uniform things. If you're able to even get some strategies, tools, if you're able to design it right for that one, then it's also a very good problem.
Okay, sir.
We have to go by literature only. Okay, when readily right, even I cannot define a problem. You may need to do some 6 months literature survey. So you understand the problem well, right? What are the gaps are available? Okay, then only right we can do it. What some functional properties you are looking for? See, that is the reason, right? Always, right? We have to make two different things like duplex process. When today I'm supposed to present, right, some duplex process related to the FSP, even because as you mentioned, that publication is difficult. I have not presented the data because that we have not yet published. Already informed to the coordinators. I have not presented the data because that is under communication. Okay. So otherwise, there's a very interesting result we got by duplex treatment. Even the reason which I kept the duplex side only, I wanted to present that very interesting data. Okay. So next time, right, anyway, when I come get the opportunity, I will present that data. Yes.
Yeah. Okay, sir. Like we are almost running out of the time. We have it's already 7:30.
Yes.
Any other queries by the participants? You can directly send a mail to sir. He has shown it in his last slide. Sir, can you maybe you can go to your last slide? Yeah,
Yes.
you participants can please make a note of this sir's email ID and you can drop questions to him because we are running out of time.
Yes.
Now I would like to quickly summarize the session because next resource person, Professor Ramji Garu, has already joined us. On behalf of our organizing committee, we extend our sincere gratitude to Dr. Ravikumar Dumpala, Associate Professor, Department of Mechanical Engineering and Associate Dean of Research at VNIT Nagpur, for his insightful and engaging session on duplex coatings for high-performance wear and corrosion applications. His expertise and depth of knowledge on advanced surface engineering techniques provided valuable perspectives for all the participants. The session highlighted key advancements in surface treatment technologies, emphasizing the role of duplex coatings in enhancing the durability and performance of industrial components. Dr. Ravikumar Garu elaborated on various techniques such as thermal spraying, surface hardening, and laser cladding, all of which play a critical role in wear and corrosion resistance. He provided a detailed analysis of how these solutions address crucial requirements, including friction and wear resistance, oxidation prevention, corrosion protection, and thermal insulation. An insightful segment of the presentation focused on the friction surface process, a novel technique for high-performance coatings. Dr. Ravikumar explained how the process involves a rotating consumable bar pressed against a substrate to generate heat and produce solid coating layer. His articulates case studies on the HVOF spraying, CVD coatings, and research-driven approach have undoubtedly enriched the participants' understanding of surface engineering and its transformative impact on industrial applications. I thank you once again, Dr. Ravikumar Garu, on behalf of our organizing committee for your valuable time and significant contribution to the session. Thank you very much, sir. We look forward to collaborate with you in the future. Thanks.
And I shared in the chart, I shared custom GPT for the surface engineering.
Yes.
So if anyone have further doubts on this topic, any topic, right, that is very well trained for all the surface engineering techniques. Okay, whatever questions you ask now also you can explore there. But anyone want to explore something in surface engineering, that GPT will give all the information. Okay, actually it's a closed GPT, not like open GPT where I trained with the material that which I closed it. Okay.
Yes, sir. Thanks
Thank
a lot.
you very much. Yes. I'm leaving now.
Yeah, thank you, sir.